Thanks everyone for attending after the coffee break. I hope you're really awake. I have a bit of content, but I try to keep it very hands-on. So indeed, my talk is about hands-on threat hunting in Elasticsearch. This year I open sourced a library or a framework to help you with this. It's called EE-Outliers. The talk will be about a few of the concepts or the principles that I implemented and the reason why I did it. So yeah, the introduction was, I think, pretty complete. That's a picture of me with my little sister and little version of myself. I learned to program at a young age. I really loved it. I'm pretty sure, though, that we're playing Jill in the Jungle there on the slide. And indeed, I'm in charge of Enviso Labs. So that's the research part of Enviso. We're a boutique cybersecurity consulting company located in Brussels, about 60 people. And we just opened our small offices in Germany. So what would I like to cover today? I want to convince you of the benefits of using statistical outlier detection. I want to introduce a framework to you. I want to show you a few examples how you could use a framework to threat hunt across the entire attack lifecycle. And then, of course, kickstart you on how you can use this yourself. Maybe a first show of hands. Who is using Elasticsearch or the ELK stack in their environment? Yeah, I noticed that there were 4 talks today about, so almost half about Elasticsearch, so it's quite impressive. So let's dive in. Why do we need statistical outlier detection, or where does threat hunting come from? I think this is pretty clear to most of you, but a small recap. First of all, detecting known bad stuff using a signature can be analyzed relatively easily. I maybe should have put that between brackets, but still, we have very good Sigma rules, Yara, IOCs, IDS hits. We have platforms like MISP to exchange information. If we fine-tune our rules, and that's not always easy, we can have a pretty low volume of alerts that are manageable to go through. Now, on the other hand, if we try to hunt for malicious activity that cannot be converted into, I would say, a very simple detection rule, it takes much more effort to do this, and it requires some statistical analysis. To put this in perspective, I would say at customers where we do threat hunting and security monitoring, if we collect, let's say, 100 million events per week, we might have a few thousand alerts that somehow we need to triage in first line. Whereas for behavioral analysis, if we don't have a very robust way statistically of looking for outliers, so for stuff that diverts from the baseline, from normal user activity, you can literally start looking at the first event and end with the 10 millionth or the 100 millionth. It's just impossible to do manually. And there are some, I would say, cheap approaches and approaches that are typically taken by threat hunters to look for statistical outliers. And who has looked at this type of graph in your environment where at one point you aggregate length of a domain name or, okay. Well, in this specific case, I dashboarded the distribution of the length of command line parameters across all the running processes in an environment, I think over 24 hours, just as for sake of the presentation. You typically have this normal-like distribution. And what's then often a reflex that we have? Where do you start looking? Any IDs or any experience? Yeah. At the big bars, yeah. What would you find there? Like stuff that's very often present or that's very... Yeah, so in this case, what we look at is around command line length 70 or 80. There's really a lot of different processes. So actually, if you look at command line length, I would say that most often, for this specific case, people would do a long tail analysis and would start looking in the tails based on a metric calculated across all the logs, for example, the length of the command line arguments. Now, there's definitely interesting stuff you can find there. And of course, the reasoning behind this is that, let's say we have a very long command line parameter for a certain process. It might contain an interesting payload, for example. So that might work. But I just took an example from our own environment in our own company. And you can see here, by the way, I'm using the super cool clicker from Xavier, so I will use this. That command is actually the legitimate execution of Slack on my own computer. So in terms of command line length, that goes well over the 200 characters. And there's just a whole bunch of parameters or configuration flags that are passed directly as a command line to Slack. I'm not super sure why they do it this way. Most of the tools directly read stuff from a configuration file and then don't relaunch Slack, but this is Slack we're talking about. So that's legitimate. It looks maybe a bit abnormal, but it's legitimate. But by grouping all the processes and the length of the command line in the tail on one graph, we might have missed that one. So that's one of the big bars where there might be hundreds and thousands or millions of events that we need to go through, so really impossible. In this specific case, does anyone recognize the payload, the PowerShell payload? What does it do? Small pop quiz. Yeah, exactly. This is a very standard payload that is generated by the Empire framework. So indeed, malicious PowerShell. Now, in this case, it was hidden somewhere in the middle of the distribution, together with probably hundreds of thousands or millions of different process execution events. So the analyst manually is not going to go through this. What's maybe a better approach is to not plot the distribution for every process combined, but to do this for each process separately. In this specific case, I plotted the exact same data, but I only extracted all the information from PowerShell execution. And then you have this distribution. So very different from what we saw previously. And we basically see that a lot of the arguments passed to PowerShell in this specific environment were much smaller than the average across all processes, typically around 10 to 20 characters or words. And you see one big line here in the hundreds. And that could be our malicious payload. So in that specific case, it became very obvious by just generating a new graph where we took a slice of the data and we only looked at PowerShell, that there's something very interesting going on that we need to look into. Now, visually, we can see if I would ask you which of those bars is malicious, even without coloring them, you would pretty quickly tell me, I would like to look into this one, right? And not the big fat chunk there on the left. We can ask a computer to do this automatically without visually inspecting this with very basic statistics like standard deviation, mean average deviation, and so on. This is the core concept why we built Outliers, so the framework that we built. It's to automate this process. So imagine you have this concept, you do it for PowerShell and it works. Well, it's pretty nice. I could just as well do it for Slack, for PowerShell, for cmd.exe, for outlook.exe. Obviously, there's potentially thousands or millions of those different graphs you would have to create. This is maybe still doable in an afternoon. This becomes more complex, and this becomes impossible. I think as an analyst, if you let someone generate these graphs, you go nuts within a few days. So building these type of statistical models automatically and looking for outliers, that's what we wanted to do automatically, and that's why we built Outliers. So introducing EE-Outliers, that's the framework name. What is it? It's a framework that offers you a set of statistical building blocks or detection models that can be used to convert a theoretical threat hunting use case or a hypothesis into a working detection case, so something that you can actually run against an Elasticsearch cluster and get results. This is something when we started developing that we really missed in our hunting approach. We were spending way too much time crafting our own queries, making our own dashboards, filtering on a certain process name like PowerShell, recreating everything, manually looking for outliers, which takes a long time. So we wanted to avoid that. I'll give you an example. So this is a threat hunting hypothesis, something that any threat hunter could come up with. And we say the hypothesis is that an exploited process is abused to spawn a malicious subprocess in order to take control of a system. So we've all seen this case where there's, for example, a vulnerability in Adobe Reader, just taking a very random application, where it spawns a few processes across, for example, the period of a week. And where one of them, cmd.exe, I would not expect to be spawned by Adobe. So something I would like to investigate. You can see already that this principle, if you want to put that into practice in Elasticsearch, we need the type of concept that I illustrated before, where we make that type of analysis for each and every single process. So in this case, one analysis for Adobe, another one for Outlook, for Slack, and so on. So how does it work? I'll show you one example of how a configuration file in the framework in EE-Outliers looks like. So we can very easily create just this block, a config file. It fits on the slide. So first of all, we define all the events we want to consider. In this case, we just select all the endpoint events. Could be a bit more fine-grained. For example, all the process execution, all the sysmon stuff depends on your cluster. An aggregator and a target, and then a way that we want to count the different events. And that's really at the core of the principle I showed you before. This is the way we implement it in the config file. So building those statistical models, the graphs that you saw, that's what we are defining here. So basically we say the aggregator, that's the parent name. So Acrobat, for example, and conhost. The target, so that those are the small buckets below. Those are then the names of the processes, so parent-child relation. And we want to count those instances within the aggregator. So that basically means that we put a big wall in between the different processes. And we want to do an individual analysis for each of those. The fact that there is a line between them, you can imagine that each of those, so Acrobat and conhost, represent a different graph from my first slide. So that's really all we need to do to statistically define our model. Then we say, what are we interested in? When do we want to trigger an alert to show to the threat hunter to investigate? We want to trigger if the amount is low, so that's a trigger on condition. So we only have 3 events here. And then a method and a sensitivity. So there we will look at the average across all the buckets. Again, only for that process. So that's the concept here. And the sensitivity is 1. So in this case, we say if the average of the events, in this case 3, is lower than 1% of all the buckets, then we will tag the event and we will tell the threat hunter this is maybe something you might want to look into. We can add a bit of sugar to the event. So this is just human readable information we will tag in the event. It's not used by the algorithm itself. But whenever we have a hit, we will then say, hey, tag it as process execution. In our environment, we also add MITRE technique references there now. For example, T244, lateral movement. The reason why it triggered, so rare child process. And then the summary, it can really contain placeholders, so the actual values of the event. So a rare child process, for example, cmd.exe from the example, for Adobe reader.exe. And then we have a simple flag that says either run it in production mode, so write stuff to the cluster, or just test it and show me the output on the interface, on the console. This is then the result, just an example. The philosophy is that we never delete or create new events, we just mutate them. So we add new fields, new dictionaries to the event that all start with outliers. And you can see, for example, the outliers.reason that we just defined. I had to black out a few things, a few IP addresses and so on. A summary, and then a whole bunch of other metrics that can help the analyst to, for example, determine the statistical confidence of a hit. So how confident was the model that this was indeed diverting from the baseline? Now, small intermezzo on how we do this in our own environment. We collect all the endpoint logs from all the laptops that we have. It's about 60 in our company. We heavily depend on sysmon and OS query for this. We have a network tab in our office, but most of our people are consultants who are on the road, so we rely on endpoint there. If there's too many people at the office, it means we don't have work, so that's a bad sign. So we go for OS query. We dump all of those events in Elasticsearch. They are enriched with asset information, with country information, and so on. And then basically we have a whole set of use cases, just like the one I showed you, but about 100 that we define for our own environment, that are then ran historically through EE-Outliers, let's say the last 7 days, and that we do each day. And the only thing it does, it adds new tags to the event. So it's never going to delete or insert new documents. It's just updating. What do we do with it? Well, we dashboard everything in Kibana. We still love the Alex tag that we get. And for some of the alerts, we have ElastAlert implemented to have a case in the Hive. So if it's a high confidence alert, for example, a very rarely observed scheduled task on one of the employee workstations, that's something that can trigger a case in the Hive. We don't do that for everything. For example, we have a very robust model that detects statistical beaconing. The problem is the model doesn't really generate false positives, but there is just a lot of software that shows beaconing behavior, like Azure Telemetrics, and that becomes very annoying if it generates 10,000 use cases overnight in the Hive. And then in the end, very important, the human feedback loop. So we build in a system into the tool or the framework to whitelist certain patterns. And it's not just a dumb literal whitelist. You can do that. But there's also a regular expression way of doing this, where you combine multiple fields or multiple observations. For example, beaconing observed for domains that are very popular in my environment, ignore those or don't tag them. It can severely help with the alert fatigue that Xavier talked about earlier. And also the models learn from the observations. So the human feedback loop it's not simply an input to the tool, but it also helps to improve the statistical accuracy of the models. That's a feature we added, I think, 2 or 3 months ago. So the result is really the dashboards you're used to. So we basically just filter on all the events that have a certain tag called outliers, and then we can dashboard all those new fields that we added. You can still have very traditional lists, like you see on the left, with the table with all the reasons. There's already a few there, like a rare outbound connectivity, a rare hash, DNS tunneling. You can see an example of a reference to MITRE that we put there. And of course, look at every correlation on the dashboard itself. So you build a few basic outlier dashboards for that, and you're good. So that's the concept. That's the way we build configuration files, how we convert a hypothesis into an actual working tool. I would like to give you a few examples in the next section on how we use this successfully at customers to hunt across the kill chain. So different phases that you're probably familiar with. I'm still using the kill chain, and we're in a MITRE house, and we also love MITRE, but this is just a bit easier sometimes to show on a slide. So let's look at a few examples. So reconnaissance and exploitation. A hypothesis, an attacker will send requests in a very unexpected format to a machine and a service that they host, in order to identify and exploit vulnerability. So basically, we want to look for signs of an attacker shooting crap at the service that looks different from the other normal accepted service requests. We can create a very simple outlier detection rule again. I'm not going to bore you with all the details again. I think I got the concept across. Let's just look again at the tree it builds, or the different aggregators. At the top level, we put a wall in between all the domains that are being queried. So in this case, we're trying to detect web server attacks. So abc.be, we make another bucket in the model for every single pod, so every single page that is being visited. And you can imagine that we are, for example, hosting a CMS. We expose it on the internet, and we want to monitor if someone is attacking it. So in this case, abc.be has 2 pods on the slide. It has CMS/login and then a logout. And then the last bucket, or the last complexity that we add to the model, is the actual URI. So I just deep dived onto the logon. You can see on the left a very legitimate query. So just a logon with a user ID and a password, that's it. And then on the right, you can see something that very obviously looks like SQL injection. Now, this is probably a bit overkill to do with threat hunting and with statistical analysis. I mean, you have a lot of IDS rules for SQL injection, but that's not really the point of the slide. It's more to show how versatile it can be. The model has no notion about SQL injection. As a matter of fact, in EE-Outliers, there's not a single reference to security or to threat hunting. So you could just as well use this for marketing or for any other purpose. So in this case, we have that suspicious request. And what do we use in this case to spot for outliers? The Shannon entropy. So it describes how much energy or how much information is there in a single request. It's suspiciously higher than the entropy of, in this example, just 2 requests, but it could be 1 million. So we can again generate an alert. This can be very effective in hunting for all types of injections. So I just showed SQL injection. We use it to detect path reversal, command injection, and so on. Brute force is also a very nice one, which will very often be quite noisy in the log. So again, the energy of a single page or a source IP will go up, and this will bubble up in the statistical model. Second example, that's more the exploitation and the installation phase. The attacker will use obfuscation and rely on legitimate system admin tools in order to install and hide their malicious activity. So think of PowerShell, the standard command line tools that you have in an environment that are used by your sysadmins or your network admins, but that are also abused by the attacker. I don't bore you with the config file. I just jump to the use case in a graph form. At the top, again, we put a wall in between the different processes. So we say we want to do an analysis for each and every single tool in our environment. So don't cross-analyze across all of the different tools, what you would typically do as a manual analyst. The next one is user division. So let's say we have the data. We have some asset info in our events. Let's say the US branch. And then at the bottom, we have the command that is executed. So in this case, PowerShell install printer. And then a payload that looks pretty fishy or pretty suspicious with an encoded payload that is malicious. Another metric that the model will use here is the length of the longest base64 encoded part of the request. Again, it has no notion of security. It just looks for encoded stuff. In this case, 420 will be much higher than 0 or the average of all of the other requests, so something we can alert on. Now, the nice thing is this just shows the example for PowerShell, but imagine any other tool that you have no clue about existing in your environment, it will automatically alert. Again, because the analysis will happen for each and every process that can go in the thousands or millions. Few examples. So looking for fileless malware. This is actually one of the use cases that we have successfully used to detect Empire payloads at our customers and in our own environment for testing. And obfuscation across all of your logs. We use this also to find, for example, remains of keys in log files, where the model says, hey, for the process OpenSSL, I suddenly see a very high entropy on a command line parameter. And we said, that's pretty strange. It was actually someone pasting in a private key on the command line, which has supposedly a very high entropy. And that's the kind of stuff that if you would build in a static use case, I would never think of to look for that. An example, again, legitimate way of Java launching on my computer. I decoded the payload before showing it on screen. It shouldn't have any passwords in there. And this again shows the strength of doing that analysis by bucketing certain processes in this case. If you would do this on a single dashboard, this would fly out and alert like crazy. However, if the Java process is observed to be launched like this on, for example, all of the employees' computers, then the model will be silent. It will learn this is just baseline behavior of Java. unless obviously your entire environment is breached before you start working with this tool. And it will not flag them as being an outlier. Third hypothesis, we move on into the kill chain, so command and control. A compromised workstation and a server could communicate to a C2 server through low-volume beaconing requests. Who is familiar with beaconing or the concept of beaconing? Yeah. Who has successfully spotted beaconing? That's more of a... Okay. Interesting. So still a very popular technique. Attackers need somehow to reach out to their home base, either to leak info or to get commands. So we are very interested in seeing this. Same principle, I think you get to know the concept. In this case, we don't look at the process at the top, but at the domain name. Below that, we bucket by host. So basically, who visited a certain domain with an internal IP. And then the next bucket is no longer a technical indicator like a command line length, but just a bucket of the hour when an event happened. In this case, you can see that the team viewer subdomain is visited quite, I would say, monotonously. If you look at the hour buckets, 10 times at 8 a.m., 12 times around 9 a.m., and so on. So the mean average deviation that indicates how different those numbers are is very low. So it looks like an automated thing, something that every 6 minutes or so is sending something back. Whereas in the example of Google, 2 requests at 8 a.m., so people start arriving at the office. 90 requests at 9 a.m., people start doing their job, aka Googling. And the mean average deviation across all of those is just super high. So it means it doesn't look automated. It looks really like user activity. Perfect. And this is actually not just an example. It's something we found in our own environment. So we don't have TeamViewer on our computers at Enviso. So I saw this specific alert triggering for that domain name. I just obfuscated the number there. And I thought, And it was the PC of our office manager. And basically what had happened, so I gave him a call. I said, yeah, there's remote administration software on your computer that we don't use. And actually your office manager was approached by the accounting firm that managed the accounting software too. And they said, yeah, we need to do some maintenance on your computer. So just install this piece of software. Now, our users are not admins. I feel you coming. But it was actually a portable version of TeamViewer. And I saw that in the logs and it made me even more worried. I was like, C downloads, blah, 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 portable version of I was like, the model works, but I'm very worried now. So this was just the accounting firm. So we verified it was legitimate. We gave a very angry call to the accounting firm and we removed the software. They were a bit lazy, didn't want to come on site to the office to do some maintenance, so no. The last one, so that's actions on objectives. We're really at the end of the kill chain now. The attacker has a footprint in the environment. He's moving laterally in the environment. He's trying to find your crown jewels. What is the hypothesis that the threat hunter can have? Well, a compromised user account will be abused by an attacker to pivot across computers in a Windows network. So typically a legitimate account is phished or is brute forced or whatever, cached credentials, so many ways of stealing an account. And we want to track that with a use case. I added a fourth layer here, and we can go as far as we want in the use case definition. We start at the top by the team. So we don't start by a technical indicator, we just start making an analysis per team. So let's say the development team. Then we look at the username, and then at the user identity. So we tell the model, don't analyze all of the logons for a specific developer. Just look, for example, at the difference between the development account he has, so the one he interactively uses, and then the domain account, the domain admin, which is much more restrictive. And we tell the model, analyze this separately. And in this case, we see that there are quite some visits from Belgium, Vietnam, and France for the developer one. And this is very typically what you see if you don't do this type of analysis, the type of false positives you have in your environment. You will have a lot of people that go on travel, they log into their computer over VPN, and then suddenly, hey, you're in Vietnam. Yeah, but I'm just logging in, I'm helping on a ticket, blah, blah, blah. So 200 events from Belgium, 40 for Vietnam, 120 for France. Statistically, this model will not trigger. It will say there's too much variety in there, so this looks pretty okay. However, for the domain admin account, we saw 40,000 events, approximately for the Belgian office, and 120 for Nigeria. While those 40,000 are all coming from a jump host in Brussels, and the admins are actually not allowed to log on to a machine directly with the domain credentials, which makes a lot of sense. But they need to go through that security host or jump host to do that. And this, of course, stands out like crazy. And if you imagine doing the analysis not at the level of the identity, but just across all of the locations, this would even be probably obfuscated or drowned into the events of France and Vietnam. That is even lower. So it shows the power that you have by having this type of layered approach in your analysis. Again, imagine doing this manually for all of the users, all of the divisions, all of the identities, all of the locations. Even for a 50-person company, I think it would take a few weeks. Just to finalize the use cases, there are a few other metrics that we support in the framework, and we're adding new stuff. You can look for outliers in the length of a value, the numerical value, but also the length, the entropy, the encoded length, obfuscation, the length of a URL specifically, and so on. There's quite a few more that I didn't cover here. So wrapping up, and now I show a few more examples where we were successful at customers to find bad stuff. Reconnaissance, so scan behavior, host enumeration, there's not so much you can do, but still. In the delivery part, so emails from unlikely sources, you can build that type of model. And a delivery targeting VIPs, so if statistically one group of users suddenly get the same message subject, something we want to look into. Exploitation, the suspicious child processes, that's something we covered in the examples. Injection attacks, also something we looked at. Fileless malware execution, again, you're a bit useless there in blacklisting and a hash, because this is just PowerShell, everyone is using it. So there it's real behavioral analysis. We look at what users do historically, and based on that we can make a decision. Other options that are very nice to have is suspicious scheduled tasks, one of the favorite ways of the attacker to gain persistence, an obfuscated command, and so on. Beaconing and tunneling. We didn't cover tunneling here, but you can also look at statistical properties of the size of a packet or of a session. That's something you can do. And then actions on objective, stuff like the suspicious logon countries, a suspicious share access. I think you get the idea. You can plug in this framework across your the kill chain. A few other features we have, or that we're building in. You can really fine-grain say how far you want to look back historically in the framework, because this takes a bit of processing time, as you can imagine. Support for email notifications, whitelisting of certain outliers is quite a powerful system. And then tagging of certain asset fields. So you can actually say, if you have a hit on a certain event and there is a field that's called source IP, then tag it, and then you can dashboard it and you can give it a certain risk score, which is nice. If you see a certain asset that is very affected across all of the use cases or a big part of them, you can start by focusing on that asset. The last part, do it yourself. So all of this is open source. We're constantly improving this, so you will see that the last commits are very recent. You can find it on GitHub. It's all Dockerized, by the way, so download, put the config file, and you're good to go. Quite some extensive documentation on GitHub. I wrote a few blog posts on how you can implement certain very specific things that we're also doing at customers, like TLS beaconing detection, or the suspicious child process example I gave in the talk today. A bit of the ongoing research. More complex means of detecting outliers. So the more complex the model is, the more complex type of statistics you need. LoveDB scan are just two examples that generate some nice graphs that I could show today. So here you're basically trying to map an outlier on higher dimensions than just to what you would typically see on a graph, an X and a Y axis. Interesting, but a bit difficult to debug in an actual use case. Buzzword bingo. So, of course, we need to talk about machine learning. We are actively working on some concept from natural language processing to use this to detect outliers. And maybe some of you are familiar with the research from Google and others around Word2Vec, Doc2Vec, that try to map a distance between the meaning of words, like king is close to queen, man is close to woman, and you can basically do calculations with those concepts and, for example, say king minus man plus a woman equals a queen. That's the type of concepts that are very nice to reason about in your statistical models. Currently, we're limited to a numerical value that you plot on a graph and where you look for outliers. An example how we could use it is, for example, services.exe being semantically closer to C Windows System 32 than to a temp folder, right? So that's the kinds of concept that we're looking into. I finished with this one. It's a blog post I published last year. It's called Going Beyond Wireshark. So new ways of visualizing network traffic. This was just a pretty basic proof of concept. But the idea is that we still spend way too much time looking at tables of IP addresses that really don't make any sense to an analyst. We look at a lot of events in a table. If I show you this, you immediately know which systems are very active. If I gave you, I think this is 500 events visualized, it would take you quite a bit more time to know that. So we're actively working on new ways of visualizing outliers, but also just in general security events. I think I'm just within my time, so I thank you a lot for the attention, and I'm open to any questions.
Thank you. And are there any questions?
Yeah.
Yeah, hello, thanks for the talk. I was wondering, at the moment, so you're, have you tried to, just use the subcategories, the grouping, you do, as a feature and let it run wide and find if it can find interesting
itself?
Yeah.
Yeah, so it's actually one of the features that I couldn't cover today, but it's there. It's called the wildcard model. You basically say, don't give a bucket, just select all the fields and look for statistical interesting stuff across all of the combinations between the different fields. That's there. That can take a long time. So if you have, let's say, 2,000 different features in a vector, in an environment of 60 computers, we easily spend 2 full days to just cover the last 24 hours. So, yeah. But that's something that's there, and it has the example of OpenSSL that I talked to you about with the certificate that came out of this. Yeah. Other questions? Yeah.
Thank you. Could you please go to the slide where we had the Shannon entropy stuff?
Oh.
Or, well, actually, so I tried to note down the numbers, but I can't really remember. I know that it was 4.14 for the accepted case, and yeah, so I don't know the exact number, but it was 4 point something for the one that you said, like, yeah, that's one that you state that it's an outlier. I can say stop, and I can, no, we still have to go for yeah. Yeah. So 492. Okay, so in this case, like you see here 2 numbers, but what would be like the distribution of like entropies for normal? Like how can an analyst say here, yeah, okay, that's 4.92, and
for an analyst,
so where do you like how because these are pretty close, so maybe like
exactly,
it would be better to like scale this up for an analyst so it's easier to spot it. Or do you have anything for that, or a different way instead of
if you would do it manually?
Shannon entropy, maybe a different way to display this.
Yeah. I think for the sake of the 2 things, for the sake of the presentation, I just show you 2 requests, but you will actually see that if you improve or increase a bit the length of this, or you change just the username, the entropy will be very, very close to that one. So this one, it's a quite a big difference. So this could be 1 million different numbers. And if there's a lot of close values to this, then the standard deviation will be very small. and it will be very sensitive to this type of change.
Okay, yeah, sorry, I'm sitting on the side, so I didn't see that standard deviation there.
Standard deviation is the metric that I use here.
Okay, sorry, yeah,
that's
I
fine.
couldn't see that number.
If you would do it as a manual analyst, a nice way to combine with this or a metric is the length of your request. You could start just by looking at the long requests.
And then check the entropy, or?
Exactly,
okay.
yeah, and work with that. Or just look at the smaller ones and look for big entropy, then it means there's a lot of information in a small string. That's something that can help you. But to be honest, doing this manually, we tried it and I failed at it. So that's the reason why I built it into the model.
Yeah. No, I just like, if I want to ever like do something like that.
Yeah.
Also, do you have in the framework, because it's, I mean, maybe it's popular among people that I talk to, but the other value that a lot of people use is Mark Baggett's value from Freak. Do you have that one also?
No, it's not. It's not in here. So the key ones I use is mean average deviation, standard deviation, the average. It's maybe someone or something we can talk about because I don't know it. So it's using a corpus that you need to digest, and then it gives you like a sort of similar numerical value, but it's based on an actual like dictionary that you need to fit in. Yeah. That's actually one where we tried to change the Shannon entropy into the popularity of numbers in the English dictionary, but we actually removed it again. The reason was that one is very tricky because it works on things where you expect words, like domain names or splits of domain names, but it falls flat very quickly for anything else. But we might consider another one that's based on
this one, the way it works is because originally he used it for speed up blind SQL injection, so that's why you need to fit in a corpus, and it checks like the likelihood that a certain letter is followed by another letter. So that's why it's a bit more like subtle, but yeah, it doesn't work all the cases, but my experience is it's better than just doing Shannon entropy.
Well, do a pull request. No.
Okay.
Cool, thank you.
I'm pretty sure Eric knows the tool.
Yeah, okay.
You can just ask him. Yeah, that's all I have. Thank you.
Other questions?
Are you planning to release a list of hypotheses?
The hypotheses are easy, but it's the implemented use cases. Yeah. So we have a few on the blog post, but we don't release everything that we create. The reason is that some customers commission us to do it. But we keep publishing use cases on the blog. Honestly, it's a very easy format. Once you understand one use case to build it for your own features, it's and anyone who is willing to try it, come to me after the talk or send me an email and I will happily help them. But we'll keep documenting things and adding new examples.
Okay, then. Thank you very much.
Thank you.